Integration by substitution using the natural logarithm. If your main function that you're trying to find the antiderivative of is 1 over f of x or some other function over f of x, you want to look at what f of x is, which is the function in the denominator, and determine if the derivative is also present in the problem. Remember, when we took the derivative using the chain rule of the natural log of f of x, we got 1 over f of x times f prime of x. So we want to make sure that whatever is in the denominator has its related derivative in the problem as well. Example 9. So notice here that we have a function over another function. That's a key tip-off that we're probably doing integration by substitution, and that this function was probably the result of taking the derivative of the natural log. So we look at the denominator, which is e to the 2x minus the natural log of x plus x to the 7th. We then find the derivative and see if that's also in our problem. So here we have 2e to the 2x minus 1 over x plus 7x to the 6th as the derivative. Notice that that is what's in the numerator of this problem. Since that derivative is present, this is a good candidate for integration by substitution. So how does this work? Now again, we're looking for the original inside function. Since we were taking the derivative using the chain rule of a natural log function, the original inside function ended up in the denominator of the derivative, which means that when we pick our u, we're going to pick our u to be the denominator of the function. So here, that means that my u is going to be e to the 2x minus the natural log of x plus x to the 7th. So now I do my side work. My du dx is going to be the derivative of that. So 2e to the 2x minus 1 over x plus 7x to the 6th, which means my du is going to be the same thing times dx. So 2e to the 2x minus 1 over x plus 7x to the 6th dx. So now when we start to plug things in, we always start by plugging in our u. So remember, we picked our u to be the denominator, so it's going to go in there. Once we have that, we want to look at what's left. So when we compare what's left to our du here, we find that they match exactly. They're not different by a function and they're not different by a constant. So instead of the numerator times dx, we can substitute in a du. So since we took everything out of the numerator, we leave a 1 placeholder and we put our du to the side. So now we've successfully turned everything from x's into u's, which means that we can now go ahead and find our antiderivative. So remember, the antiderivative of 1 over a variable is the natural log of the absolute value of u. So we don't want a u in our final answer, so we substitute back in what u represented. So we have the natural log of e to the 2x minus the natural log of x plus x to the 7th. So once we've substituted our u back in, we have found our antiderivative for this function. So again, some of the key things that are happening here with the natural log is that we first notice that the thing that we were integrating was one function over another one. That was our first clue that not only were we doing integration by substitution, but it likely came from the chain rule of the natural log. So let's look at another example. Example 10. So we notice here again that we have one function on top of another function. So that's our clue that here we're probably doing integration by substitution and we're expecting our resulting answer to be some form of the natural log. So again, we're going to pick our u to be the function that's in the denominator. So here, that'll be sine x plus e to the x minus x to the 6th. Now we need to take the derivative of that function. The derivative of sine is cosine. The derivative of e to the x is e to the x. And the derivative of x to the 6th is 6x to the 5th. So now we need to multiply up the dx. So we have cosine of x plus e to the x minus 6x to the 5th dx. So again, now that we have our du and our u, we can start filling in our substitution. So we always start with our u. So u is going to get plugged into the denominator. That's how we picked it. And then in the numerator, we notice that there's a cosine x plus e to the x minus 6x to the fifth, and we have a dx. So we compare that to our du, and we notice that that's exactly our du. So we don't have to manipulate any constants. So that means instead of the function we have in the numerator times dx, we just have 1 du. So here we have 1 in the numerator since we took everything from it, and the du is off to the side. Because again, the du is an operator that tells us what our variable is. So now, the antiderivative of 1 over u is going to be the natural log of the absolute value of u. We don't want a u in our final answer, so we substitute back in. So that's sine x plus e to the x minus x to the sixth. And again, when you substitute back in for u, make sure that you're using the u that you had written down when you were doing your side work. Sometimes we accidentally plug in a du or some other function, but as long as you're labeling everything carefully, you should be able to avoid just a silly mistake. So now we have our antiderivative, which is in the form of the natural log, which is what we were expecting since we were finding the antiderivative of one function over another one. Let's look at another example. Example 11. So here, again, we notice that we have one function over another. So in this form, we're expecting an answer that is the natural log form. So when we have one function over another, we feel like we're likely going to be doing integration by substitution. So we pick our u to be whatever function shows up in the denominator. So here, that's my x squared minus x to the 10th. The derivative of that is going to give me 2x minus 10x to the 9th. So my du is 2x minus 10x to the 9th dx. So again, I now start to do my substitution. I start by plugging in my u for whatever I substituted it in for, which is the denominator in this type. Then I look at what's left in the numerator and compare. So in the numerator, I have an x minus 5x to the 9th. My du, however, is 2x minus 10x to the 9th. So my functional part looks the same. I have an x to the 1 and an x to the 9th, but my constants look different. So I have to think about how I can manipulate these to make them match. So my first step, I'm going to factor out a 2. If I pull out a 2, I'm left with an x minus 5x to the 9th dx. Well, that's what I want, x minus 5x to the 9th. So that means I need to divide both sides by 2 to get rid of it on the right. So 1/2 du equals x minus 5x to the 9th dx. So now that that matches exactly on the right-hand side, I know that I can substitute in a 1/2 du. So I'm going to put my 1/2 in front because it's a constant. My numerator got picked up as part of the du, so I have a 1 du over here. Again, you don't have to pull the half to the front if you don't want to. You can leave it in the numerator or next to the du. You just have to be careful about how you treat your constant multiple. So now I know I'm going to have 1/2 times the antiderivative of 1 over u, which is the natural log of the absolute value of u. I don't want my u in the final answer, so I'm going to substitute back in what it represents. So that's x squared minus x to the 10th. That goes inside the absolute values. So again, we expected a natural log answer because of the form of the question, and we were able to find one. And the only sort of extra thing we had to do here was in the du step, we had to manipulate the constants to match. Let's look at one more example. Example 12. So here we have a sort of tricky situation in the substitution. This one is a bit harder than the other ones we looked at. It has sort of a special trick to it. So I want to make sure we see one that's a little bit on the harder side. So normally when we have this type of situation where we have the ratio of functions, so one thing over another one. We know we want to do integration by substitution, but our u is usually the entire denominator. Now, if we tried to put the entire denominator there, we would need to end up doing a product rule to get our derivative. And we can notice really quickly that our numerator does not have things that would result from a product rule. So something's not quite right here. Turns out that our u in this case is going to be the natural log of x cubed. And this is sort of a special case because when we take the derivative of the natural log, we end up with something over something. So here, when we take the derivative of this function, we're going to do a quick chain rule. So we end up with 1 over x cubed times the derivative of the inside. So I'm doing this all without writing out my substitution steps because I think by now you know them. So here we can simplify this. So we have 3x squared over x cubed. That's the same thing as 3 over x. When you simplify, the 3 goes in the numerator and the x squareds cancel, leaving you with just one x in the denominator. So that means your du is 3 over x dx. So now let's rewrite this real quick. 1 over the natural log of x cubed times 3 over x dx. I pulled this term out and just multiplied it, right? I didn't change anything. I just algebraically manipulated it. And I did that so we can more easily see our substitution. So since u is the natural log term here, we have 1 over u. And then our 3 over x dx is exactly du. So we substitute that in. So here, again, when we take the antiderivative, we get the natural log of the absolute value of u. And here when we substitute in, we get the natural log of x cubed. So this one's a little bit tricky, but hopefully you were able to see right away that we didn't need the entire denominator. You may not figure out exactly how we'd pick our u, but you should have realized if you tried to do some of the steps of the process that our du wouldn't match up if we had picked the entire denominator. So we have to pick a little more carefully, and this is the way to do it.